Hi again, everyone. Just thought it might be useful to talk through the solutions for the Mandelbrot set examples with tasks and nested parallelism. So this is a solution for the tasks version. So basically just do fairly simple one. So just using the parallel master pattern. So the create parallel region, and then the master thread is going to generate all the tasks. And so in this version, I've chosen to put the task construct outside the J loop. Okay. So you have a choice here. You can put the task inside the J loop, but you should find that that doesn't actually scale terribly well, because you end up with a lot of fairly small tasks. So this version tends to be a bit better because there are bigger tasks. So what do we need here? Okay, care about the data attribute scoping. So Z and C need to be, you basically just need a private copy for every task, because it's basically a temporary variable inside this loop. They're going to be assigned before they're used, so we don't care about any initial values of them. The thing we do care about capturing the initial value is the value of I. So I need first private I here in order to capture the value of I from the value in the master thread when the task was generated, and then that's what will be used here when the task is executed. And as far as num outside is concerned, well, that would naturally be a reduction variable if we just had a loop version, but we can't. Well, I'll show you in a minute how to handle that, how to handle a reduction with tasks, but I'm not allowed to simply declare a reduction on the parallel region and then use that variable inside tasks. That's not permitted. So we'd have to get around that. Have to get around the synchronization or the avoiding the race condition on the update to num inside somehow. So a simple way of doing it would be to make num outside shared on the parallel region, also shared with respect to tasks. So all the tasks are accessing the original storage for num outside, but they're doing it with an atomic directive to protect the update. I mean, you could do a bit better than this. You could, so this is doing an atomic update for every iteration of J. You could accumulate a partial sum for the J loop inside the task, and then just have one atomic update at the end of the J loop, at the end of the task, would reduce the number of atomics. But for this particular example, the atomics are not particularly bad, but in other cases, you might want to reduce the frequency of the atomic updates. So the way that we can handle reductions on tasks is to use task group. Okay, so this is a relatively new feature in OpenMP, and you may still find that some compilers don't support this syntax. I suspect it's probably better by now. As long as you're using the latest version of compilers, then you probably have a good chance that this works. So what you need to do is you have to introduce a task group construct that's going to contain all the tasks where you want to access the reduction variable. And then you have to say task group with task reduction clause. Okay, so that just that basically has the same Same syntax as the normal reduction clause. So we just say it's an addition reduction on num outside. But then we also have to specify which tasks are going to contribute to the reduction. So tasks which access num outside have to have this in reduction clause on them. This is basically this turns out to be a little bit tricky to implement reductions with tasks. So my friends who do, or people that I know who do OpenMP implementations have told me, because otherwise otherwise in principle if you just declare something as a reduction, then in principle every single task needs a private copy of the variable, and it's difficult for the compiler to determine which tasks are actually going to access in principle it can't really tell without on its own which tasks are going to access the reduction variable and therefore actually need a private copy. So you can end up creating otherwise you would end up creating lots and lots of private copies that you didn't need internally in the runtime. So that's the syntax for handling reductions in tasks. And then finally, there's the nested parallelism version. Okay, so in this case, it's relatively straightforward. Just have a parallel for on the I loop and then another parallel for on the J loop. Then just again the tricky bit is the data attribute scoping. So basically, so again, C and Z can just be private because you just need they're temporary inside the J loop. So that's fine. So I needs to be shared on the inner parallel region. So this is one of these cases where, because I is the loop iterator for the outer parallel loop, so with respect to the outer parallel region, I is private. Okay, every thread has its own copy of I. But when we come to the inner parallel teams, we want all the threads inside the parallel region to see the current copy of I in the thread that created the inner team. So that means that I needs to be shared. So again, it's useful to think about shared as in this case, it's useful to think about shared as meaning use the existing storage with that name when this construct was encountered. Okay, so in that case, that means that I inside the inner parallel region is going to be the existing private copy in the belonging to the thread in the outer parallel region that created this instance of the inner one. And we can still handle num outside in this case with reduction clauses, but it turns out if you think about it, then you need a reduction at both levels. Okay, so what's going to happen here is that reduction here is going to create a private copy for every thread at the outer region. And then declaring it again on the inner parallel region, we're going to get a private copy for every thread in the inner parallel region to do its partial sum into. But then this innermost reduction will result in the result of the innermost reduction will go into the corresponding private copy in the outer parallel region. And then finally, at the end of the outer parallel loop, all the private copies with respect to the outer parallel region will then be added together. So you basically have a nested reduction going on here. And then finally, we need to think about the load balancing here. So this problem is not well load balanced because of this break statement here. Okay. So, and it turns out that for points that are inside the Mandelbrot set, this innermost loop runs the full length of max iterations. For points that are outside, this break tends to occur fairly quickly after, say, less than 10 iterations. in most cases. So for points outside the loop, this inner loop contains a lot less work than for points inside. Depending on where we are in the complex plane, this loop takes very different amounts of time to execute. So that means that both the I loop and the J loop are poorly balanced. So you need a suitable schedule on both levels of parallelism here to get sensible load balance. Okay, did anybody have any questions about that? So Dependent asks, we can use collapse here? Yes, absolutely. Okay. So for this particular example, it would be much more sensible to use collapse for this case, because it is a perfectly nested rectangular loop nest. So yep, or collapse 2 would be a good solution here. You probably won't see it giving you any performance benefit until you get to very high thread counts. Okay, so if you go up to, I mean, you can if you're on ARCHER2, you can run up to 100. You can sensibly run up to 128 threads on a node, and so using because of the load balance problems, then you might find that by the time you get up to 64, 128 threads, then collapse starts to help a little bit, but it really won't make any difference for small thread counts. Okay, good. So please feel free just to carry on with the practical exercises, and if you've got any problems or questions, please just ask.